fact, atoms show up in almost every science class you take. It makes sense. They make up everything. And they make up you. They make up me. And what could be more important than that? But how often do we actually take this deep dive? How often do we zoom right into the face of an atom and say, what really makes you tick? What is it that explains the amazing complexity and beauty of all the different things that we see in the world when they all start out with these little tiny fuzzy globs that make up everything? How does that stuff turn into all this beautiful stuff? So this chapter is all about getting really up close and personal and friendly and cozy with atoms. Okay? First things first, we of course need to discuss the quote of the week, and it's from somebody who I wish was my aunt. I love her a lot. Mad respect for Oprah. She says, "Be thankful for what you have. You'll end up having more. If you concentrate on what you don't have, you'll never, ever have enough." Which makes sense. When you focus on what you don't have, the way that brains work is they always are able to compare things, right? You're always able to have something plus one, something plus one. So no matter how incredibly lucky or abundant your life might be, you could always have abundant plus one. And if that is your programming, if that's the story you're telling yourself, you'll never be complete, fulfilled, happy. So, and Oprah knows because she, what I think is like the first talk show billionaire, something like that. Okay, why do we care about this atom stuff besides the fact that it makes up everything in the world, including us? There's one interesting application in the medical world is the miracle of laser surgery, right? So using a mixture of CO2, N2, and sometimes helium carbon dioxide lasers emit a wavelength of 10.6 micrometers. At power outputs of 0.1 kilowatts, such lasers are used for surgery. How cool is that? You don't even have to use a scalpel anymore. You can just use little lasers. How many photons per second does a CO2 laser deliver to the tissue during its use in an operation? And what does this have to do with atoms? Well, as you probably know, and as you're going to find out in this chapter, that anytime you excite an atom, when the excited electron falls back to its ground state, it releases light. And that light can be harnessed, as in the case of a laser surgery, and used to, make incisions and cool medical type things. All right, now, here's the thing. There's no way we can really appreciate and fully understand atoms until we understand quantum mechanics. Okay, so in order to understand atoms, why the orbitals where they are, and why they have the energies they do, there is some quantum mechanical principles at play. And so over the next few slides, we're going to start discussing some of those quantum mechanical principles. Okay, if we're talking about history, it should probably a good time to mention the fact that our knowledge of atoms is surprisingly young. It's kind of amazing that we've been able to, use and manipulate atoms to be able to split them, for example, in the process of nuclear fission, despite how short we've actually been aware of their existence for sure, and also even shorter amount of time that we've known, the dynamics inside of an atom and how an atom actually works. So, for example, in 1905, Einstein published a few papers, and shortly thereafter won a Nobel Prize for one of those papers, and that paper was about Brownian motion, which is a process that lent a lot of confirmation to the fact that atoms exist. So that means at the beginning of the 1900s, okay, the decade in which I was born, I guess not many of you were born in that decade, or century, but at the beginning of that century, we were not even sure atoms existed, let alone knew how exactly they were made in what the anatomy of an atom was. So that's just a kind of, brief appreciation of how quickly and swiftly science moved in the 1900s to kind of explore the structure and function of atoms. So I said we're going to have to start talking about quantum mechanics, and it started really with this fellow named Max Planck. Okay, and around the turn of the century, from the 1800s to 1900s, there was a really strong push to make more and more efficient light bulbs. All right, it was just about efficient light bulbs, and so these companies would be like, what temperatures create the most white light for the least amount of energy? And so Max Planck is doing these experiments with all these different temperatures to see, what the luminosity is. And he starts to realize, as he's like modeling, trying to model this curve, that the way he's looking at it, that if light really is just this continuous stream of frequencies, then there would be something called this ultraviolet catastrophe. Meaning if you added up the energy of all the light for any emitting body, okay, you would eventually get an infinite amount of energy, which would be impossible because it would mean that every radiating body was radiating an infinite amount of energy, and you knew that couldn't be true. And so he did a little fancy footwork with his mathematics, and he realized that light, in fact, is not a continuous stream as we thought it was. In other words, actually light comes in these little packets of energy, right? These quantized packets. And the energy of these quantized packets is given by E, energy of the photon, equals hf, where h is Planck's constant. It's the constant that he invented. He didn't invent it. It was already in nature, but he realized that this constant determined exactly the energy that you needed for these photons, and that value was 6.63 times 10 to the minus 34 joule seconds. Okay? So instead of having all the different energies for all the different wavelengths, it's actually these discrete packets of HF. All right? And so now we know that anytime we see light, we can think of it as coming in these discrete amounts. And these discrete amounts are called quantum, and hence the birth of quantum mechanics. Now, let's do a little example using this relationship to solve a question. Okay? Blue is my favorite color. That is because blue is the greatest color ever invented. What is both the frequency and energy of a photon with a wavelength in the blue part of the visual spectrum? Okay, let's start with the energy. So the energy of blue must be h times f, right? We also know, though, that frequency, right, is equal to c over lambda from remember, the speed of light equals frequency times lambda. So frequency is c over lambda. So I can replace this formula very easily with hc over lambda. And I also happen to know that blue light is a wavelength. So lambda for blue is about 470 nanometers. All right? So then I can easily find this energy by saying the energy of the photon is equal to 6.63 times 10 to the minus 34 joule seconds times the speed of light, 3 times 10 to the 8 meters per second, divided by 470 times 10 to the minus 9, and I get an energy of 4.2 times 10 to the minus 19 joules. Cool? So this would be the energy of one single blue light photon, the smallest bit of blue that you're capable of actually receiving. Okay? One interesting thing when we're talking about this realm of physics is that this is a big number, and it's kind of annoying to always have to deal with this big number. So often electrons and atomic energy levels are measured in something called the electron volt. So I'll write it up here. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. It's derived obviously from the charge itself. So if I wanted to frame this energy, this photon, in terms of electron volts, I would just go ahead and divide by 1.6 times 10 to the minus 19 joules. And I get 2.6 electron volts. That's much, much easier to deal with than this. So now you know exactly how to convert into electron volts whenever you need to, and you have a more simple way of expressing the energy of photons and the energy levels inside of atoms. All right. What is the frequency? That this problem also asks the frequency. Remember, frequency is just c over lambda. This is 3 times 10 to the 8 meters per second. This over here is 470 nanometers. And when I put that in my calculator, I get a frequency of 6.4 times 10 to the 14 hertz. Okay? All right. So that's blue. Very simple relationship to deal with. If you don't have the frequency, you could always substitute the speed equation and get it in terms of wavelength. Simple. Okay, let's do question number 1. Which of the following is necessarily true? Red light has more energy than violet light. Violet light has more energy than red light. A single photon of red light has more energy than a single photon of violet light. A single photon of violet light has more energy than a single photon of red light. None of the above, or a combination. What do you think? Okay, so red light and violet light, as far as A and B is saying, is talking about it in general. You don't know how many photons you're talking about. You don't know anything about the intensity of it. So A and B is gone automatically. But we can use this relationship to make claims about an individual photon, right? And so what has a longer wavelength? Red light. What has a shorter wavelength? Violet light, right? Violet light, if it has a shorter wavelength, right, if this goes down, that means energy is going to go up, right? Denominator goes down, numerator goes up. So this would imply that a single photon of violet light has more energy than a single photon of red light. That is the only thing we can determine is true, because as far as A and B are concerned, we don't know how much red light, how many photons we're talking about, and we don't know how many photons of violet light we're talking about either. So that's that. In the next video, we're going to take this to the next level. So it turns out that, oh, this is so crazy. It turns out that if light can behave like particles, photons, what if matter can behave like a wavy light? And that was the real breakthrough, and that you'll see is going to have amazing consequences for atoms.